Thanks for having me here today. My name is Lucius Huang from Division of Software at Yonsei University. Today I am excited to share our research on a critical security issue in wireless systems. The title of our paper is Adversarial Robustness Analysis of Deep Learning-based Automatic Modulation Classification. As you know, deep learning has revolutionized automatic modulation classification, which is called AMC. However, today I want to discuss a less explored but a vital question. How secure are these models against malicious attacks? To understand the problem, let's take a look at a classical example from computer vision. On the top left, we have a panda. To us, it clearly looks like a panda. However, if we add a tiny amount of carefully crafted noise, which is invisible to the human eye, the AI model suddenly identifies this panda as a gibbon with 99.3% confidence. We apply this same concept to wireless signals. You can see in the bottom, we start with a standard AM signal. By adding a minimal adversarial perturbation, we created an input that looks identical to the original signal. Yet the deep learning model is completely fooled and classifies it as a QPSK with 99.5% confidence. This highlights a severe security gap. If an attacker can spoof modulation types this easily, they could evade spectrum monitoring or disrupt military communication without being detected. Now let me explain our experimental setup. For our dataset, we use RadioML 2016.10a, which is a standard benchmark for AMC research. It contains over 200 to 20,000 samples of IQ data, covering 11 different modulation types. The dataset spans a wide range of signal-to-noise ratios, from minus 20 decibels to plus 18 decibels. For the model, we utilize VTCNN2 architecture. As shown in the diagram, it consists of two convolutional blocks followed by fully connected layers, totaling approximately 500,000 parameters. This is a lightweight yet powerful model widely used in this domain. To test its robustness, we employ these representative attack methods as FGSM, DeepFool, and CNW. FGSM is a fast but single-step gradient attack. DeepFool is an iterative method that finds the minimal perturbation to cross the decision boundary. CNW, a sophisticated optimization-based attack. Before you break the model, let's see how it performs in clean environments. This graph shows the classification accuracy across different SNR levels. As you can see, the performance follows a sigmoid-like curve. At low SNRs, the model struggles, which is expected due to high noise. However, as the SNR increases above 0 decibels, the accuracy rapidly improves and plateaus at approximately 80%. The overall average accuracy across all SNR is 54.02%. This confirms that our baseline model is well trained and functions correctly under normal conditions. However, the situation changes drastically when we introduce adversarial attacks. Please look at this table. It compares the accuracy of the clean model against the three attack methods. The clean accuracy is about 54%, and accuracy in a condition of FGSM attack is about 17.6%. In the CNW condition, the accuracy is about 29.4%. In DeepFool, we have 10.8% of accuracy. Considering there are 11 classes, 10.8% is essentially random guessing. This proves that our model is extremely vulnerable. DeepFool in particular was the most effective because it precisely calculates the shortest path to push the signal over decision boundary. So why is the model so easily fooled? This slide illustrates the geometric reason. Imagine the decision boundary between QPSK, which is blue in this image, and 16 QAM, which is considered red in the feature space. The model learns a boundary that separates these classes well enough for natural noise. However, an adversarial attack like DeepFool finds the weakest link in this boundary. It applies a minimal perturbation vector, like the red arrow right here, that is just long enough to push the data point into the wrong region. This tells us that while the model is robust to random noise, it has a geometrically fragile boundary against targeted manipulation. So how we defend against this? We evaluated two defense mechanisms: adversarial training and denoising autoencoder. Let's look at the results in the table. First, adversarial training in the middle row. We trained the model using data-augmented FGSM examples. This successfully improved robustness against FGSM, raising accuracy from 17.6% to 33.5% over here. It also provided some transferability to CNW, improving it to 40.7%. However, notice the trade-off. The clean accuracy dropped slightly from 54.0% to 51.5%. Second, the denoising autoencoder. We used a DAE as a preprocessing step to clean the signal before classification. The clean accuracy was well preserved at 53.9%, but it failed to defend against the attacks. FGSM accuracy remained at 17.5%, and DeepFool only improved slightly to 21.2%. So, why did DAE fail for wireless signals? The answer lies in the fundamental difference between images and RF signals. In images, adversarial noise is often high frequency, while the semantic content, like the shape of panda, is low frequency. A DAE can simply smooth out the noise. In wireless signals, the semantic content is defined by fine-grained changes in amplitude and phase. These features are often high frequency, just like adversarial noise. When the DAE tries to smooth the signal to remove the attack, it simultaneously destroys the modulation features needed for classification. It effectively learns an identity mapping, preserving the attack rather than removing. So let me summarize the main points. First, vulnerability. Deep learning-based AMC models are highly susceptible to attacks. We saw accuracy drop to 10.8 under DeepFool. The second one is defensive. Adversarial training is currently the most effective defense, though it comes with a trade-off in clean accuracy. So, standard denoising methods such as DAE are ineffective for wireless signals because modulation features are too similar to adversarial noise in the signal domain. So moving forward, we need to develop domain-specific defenses that respect the structural properties of RF signals rather than just borrowing techniques from computer vision. This research highlights that we deploy AI in wireless communications. Securities cannot be an afterthought. It must be a core design requirement. Thank you very much for your attention. I'll be happy to answer any questions you may have. Thank you.